Great. Welcome to our last lesson of our third unit. So this is lesson 6, double angle identities. So these are the ones that I definitely use the least often in terms of just general questions that you come across. So I'm definitely the most rusty on them. So you'll notice I'm going to be dragging them around with me on the pages so I can constantly refer back to them. Again, in your notes, having a formula sheet printed out is not a bad idea. You can get that from our Office 365. You can also take a picture of it with your phones if that's more the way you want to go. Whatever you need to do so that you have access to these identities. And again, they are all on your formula sheet except for the ones from our very first lesson on identities, lesson 3. So lesson 4, 5, and 6 you'll have access to on your formula sheet. But we'll jump right in and do some examples. So the first one we're looking at, example 1, is just write each expression as a single trigonometric ratio, then evaluate where possible. So the key thing to note is that these first two, you could hypothetically just try and tackle them and evaluate them without doing the single trigonometric ratio. But because the question explicitly says that that should be your first step, that's what we're going to do. And it helps us kind of ease our way into using these identities. Excuse me. So when I look at this first example, A, I notice cos squared and sine squared of the same angle. So when I go over here, I look at that and I'm like, well, that's not a sum or difference identity. It's not my Pythagorean identity because that's sine squared theta plus cos squared theta equals 1, and that's not what we're dealing with here. So it's something different. So I check out my double angle identities and I see cos squared alpha minus sine squared alpha equals cos 2 alpha. So this would be an identity where instead of writing this value here, I'm going to write what's on the left-hand side. So instead of all of this, I can simplify it to be cos of 2, and then the value of my angle, which in this case is pi over 4. Then I'm going to put square brackets around that so I remember that all of that is fitting inside my cosine function. Once I've got that, I've fulfilled my first requirement of my example, and so now I can solve. So this is really asking me for cos of pi over 2, and we know that cos is our x value on our unit circle, if you want to think about it like that, or if you just have your values memorized, that's fine too. So we're looking right here, and our x value is 0, and so that would be my final answer for evaluating. Looking at the second example, this might look a lot like one of our sum and difference identities for tan. So just looking back at that really quick, we see that we have two different tans of two different angles. So one way that you can really identify a sum and difference identity versus a double angle identity is the fact that that value plugged in for your angle, or just the letter plugged in for your angle, is going to be the same in all instances. That's when you're dealing with double angle identities. So we're dealing with tan. There's only one option for tan. The only tricky part is that the bottom is written backwards, which means that my signs are switched. When it is negative instead of positive, tan is positive instead of negative, which means that this whole thing first needs to be adjusted. So before I even start substituting in anything else, I need to make sure that that's in the correct order to match my identity. So I'm going to pull out a negative or add a negative in, whichever way you want to think about it. My numerator needs to be staying the same, so I'm not going to do anything there. But I do need to change my denominator. So again, I've written that negative out in front. You could have also written it in the denominator. Maybe that will help make things more clear. So then if I take a negative out of there, I'm left with 1 minus tan, or if I want to write it in the same order it shows up here, I've got negative tan squared pi over 6 plus 1. And so see how I've changed those signs, and now they mirror the signs that are in the denominator. It's in the different order, so you could also rewrite it. and bring that negative out in front if you wanted. That's my personal preference, but again, it's totally up to you. 1 minus. Okay, now that I've got it looking exactly like my identity here, now I can feel truly confident in subbing in my left-hand side of that identity, that simpler tan 2 alpha. I'm going to put pi over 6 in place of alpha because that's my angle value. And this negative is not part of this equation at all. And so what I'm going to have to do is that negative is still going to have to kick around. So because I'm running out of room, I'm going to do some mental math here, and I'm going to say this is actually the same as pi over 3. So if you need to remember that, pi over 3. So tan of pi over 3, if I think of my unit circle, I think of that table, however you remember your unit circle and special angle values, that's going to be root 3, should be what just tan of pi over 3 is. But again, that negative just kind of keeps hanging around and loitering, so it's going to be negative root 3 is my final answer. Even though technically when I work with just tan of pi over 3, I'm in quadrant 1. My last one here, I see 2 sine and cos, and I'm not even looking at my angles because the second that I see this one, there is only one identity that looks remotely like that, and it is sine of 2a. So what we see there is we can say that this is the same as my identity, so I can plug it in instead as sine of 2 times 5t. Unlike our first two parts of this example, where we had actual values in place of alpha, here we just have a different letter, or a combination of letter and number, a different polynomial. So I just can simplify it. I can't actually finish evaluating. So I'm going to stop at this next step where I say 10t, because I literally can't do anything with that because I don't know the value of t. So that's where I would stop here. Okay, so I'm going to take these with me. As I go to the next page so I can keep referring to them, because I find them a little bit tricky to remember. So example 2, given angle theta is in standard position when it's in with its terminal arm in quadrant 4. So already I'm going to kind of sketch a picture for myself that I'm looking in quadrant 4. And cos theta equals 2 over 5. So remembering again from SOHCAHTOA that we're dealing with adjacent and hypotenuse. So whatever this looks like, my triangle does not need to be perfect as long as I have like a reference point. This is theta, and I'm talking about adjacent over hypotenuse, so 2 over 5. Determine the exact value of each trigonometric ratio. So before we can do anything, I'm going to have to determine what is theta, and then I can work from there. So in order to be able to figure out theta, or at least the ratios that I can use for my different trig functions, I am going to need to solve for my missing side. So that's what I'm going to do first. And we've done this in previous lessons, especially working back in like lesson 2. We saw some examples like this, and I warned you that this would come back and definitely probably will be a question on the provincial exam. So in order to find this missing side, I'm going to set up my Pythagorean theorem. 5 squared equals 2 squared plus, and I'm going to say y squared because it's my vertical side. I'm going to move that 2, so 25 minus 4 is 21 equals y squared, and so y is the square root of 21. And it'll be negative because it's going downward. Okay, once I filled that in, now I don't even need to solve for theta because I can use all my general trig functions and my identities. So when I go to work through A, so that's all before I even try and attempt these individual pieces. Now I'm going to go at them. Well, I don't know theta, so I can't just plug and chug. I'm going to have to use my identity. So I'm going to work with 2 sine theta cos theta. From here, I know the value of sine theta is opposite over hypotenuse, so it's going to be negative root 21 over 5. So I'm going to write that in its place. And I know the value for cos, we're told in the original question, is 2 over 5. From here, we're going to multiply this all out, and my final answer would be negative 4 root 21 over 25. Okay, and again, I'm not plugging these values in for theta because they are literally the ratio associated with sine of this particular angle. So do not write sine of root 21 over 5. That is bad news bears. Okay. Cos of 2 theta, you have a ton of options here. I personally always default to an option that lets me work with the most values that were given in my question originally. So when I look, I've got 3 different identities that I can plug in for cos of 2 alpha, but only one of them only includes cosine, which is actually straight up given to me in the question. So that's the one that I'm going to work with, because then I don't need to worry about, like, what if I made a mistake here? What if I subtracted when I should have added, or vice versa? There's a million things you can do wrong arithmetically. So if I default to what's in the question as much as possible, my chances of having those little mistakes are far less likely. So I'm going to go with the middle one here, this 2 cos squared a minus 1. And again, I know what cos of theta is because it's told to me in the question. It's 2 over 5 squared minus 1. So this is 4 over 25 times 2, so 8 over 25 minus 1. Common denominator, that's going to be 8 minus 25 over 25, or 17 over 25 negative. And there we go, evaluated just like that. So it might seem daunting, but this is actually way more related to grade 10 trig, and then just being able to plug into a formula is the only thing that's new. Oh, you know what, I'm going to grab those identities, bring them with me. I have them to refer to. Okay, so example 3, prove that cotangent of theta equals 2, or cos 2 theta plus 1 divided by sine cos, or sine 2 theta. So again, I'm not going to work with the left-hand side because the left-hand side is way too simple, and I have no idea where I would even begin to try and generate these identities from one single trig function. So instead, I'm going to work with the right-hand side. Because I can distinctly decide that here, I'm going to work with this notation instead of that table format. You are always welcome to use the table format if you want. Just in this particular case, I feel like it would be more of a waste of space than anything else. So right away, I need to get rid of this 2 theta because it's not on my left-hand side. So I'm going to jump to my identities right away. And I'm going to work with my denominator first, because there's only one option. I have to choose 2 sine cos. I'm not going to use alpha. I'm going to make sure I use theta so I don't change my variable from the question. And from here, I'm going to look and I'm like, okay, well, remembering that cotangent, so maybe making a side note to myself, that cotangent is cos theta over sine theta, I need to remember that I'm going to need to eliminate this cos theta in the denominator. So I'm going to choose the identity that lets me have a cosine in the numerator to get rid of it. So automatically I'm not using this bottom one. Okay. From there, I also know that I don't really need sine theta at all in the numerator because I want to end up with cos theta in the numerator. So because I know I want a cos left over in the numerator and I need to cancel out with a cos in the denominator, both of those pieces are telling me use the middle identity here. And remember, that's only going in for this part, so I need to still remember to put that +1 at the end. And that's always nice because those two pieces cancel out right away and create an opportunity for more canceling. So right away I see that goes away. I also see this goes away, the square goes away with the other cos in the denominator, and I am left with exactly what I said I wanted, which can be written as cotangent theta. And so my left-hand side is equal to my right-hand side. Huzzah! Okay, so again, if you want to give this one a shot on your own, just pause the video. I will work through the full solution strictly because this is a challenging concept, the idea of identities, and I can explain my thinking as I go. But feel free to pause and give it a try on your own. So I'm again going to work on the left-hand side first because that's where my double angle is showing up. And I don't like double angles because I don't have any on the right-hand side, so I need to make it disappear. First thing I'm going to do is, because these are both inverse identities that we learned about in lesson 3, I'm going to switch them to our like kind of fundamental three trig functions. So I've got cotangent equals, I'm going to say left-hand side equals cos over sine times 1 over sine 2 theta. From here, I know I need to get rid of that double angle, so I'm going to rewrite this again. Instead of sine 2 theta, I only have one option, so I'm going to use 2 sine theta cos theta. Now I can multiply things together and look for pieces that cancel. Those coses cancel. I've got 2 sines in the denominator multiplying together, and so I can simplify this to be 2 sine squared theta, and that's exactly what's on my right-hand side. So left-hand side equals right-hand side. Yay, and I'm done. So it might seem intimidating. This might look monstrous to start with, this kind of set of identities for double angles. And they're trickier to remember because there's just lots of little details, remembering squareds, remembering subtraction, remembering order of things. So again, that's why you're given them on your formula sheet. But in terms of knowing what to do with them, you're kind of in luck because our ultimate goal is usually to get rid of that double angle. So you're going to be working with trying to plug in what's on the right-hand side to get rid of what's on the left. Again, the only exception being what you saw in that first example in this lesson. So when I look at this question, example 4, solve the equation over the domain of 0 to 2 pi, not including 2 pi. I can glean a couple things. Number 1, I am solving the equation, so I actually want to know what is x. So I should end up with x equals at the end. And I'm also working in radians. All right, so once I have established that, I'm going to just rewrite my equation so it's in a workable space. So again, it's sine double angle, which means I only have one option to choose from, and so I'm going to use that. 2 sine x cos x minus cos squared x equals 0. So the half and 2 go away, leaving me with sine x cos x minus cos squared x equals 0. Now, you could go into the idea of using your Pythagorean identity here as well and turning this into sine, but the bigger problem here that we're facing is that we have both sine and cos showing up. So you can do a couple different things here. My first instinct would be to try and factor out one of those cos x's. Okay. Once I've factored that, now I can work with individual pieces, those separate factors. So I can easily solve cos x equals 0. That's simple enough. That's part of my set values. It's part of my unit circle. So I think back, when is x 0? And x is 0 at pi over 2 and 3 pi over 2. So that's great. My other factor, sine x minus cos x equals 0, becomes a little bit trickier. So I'm going to rearrange it. And sine and cos are typically equal when my angle of reference is pi over 4. And this happens when they're both positive and they're both negative. So in quadrants 1 and 4, which means that x is going to be pi over 4, but also 5 pi over 4. And again, that's quadrant 3 when they're both negative. And that's how I would solve this. You could try a different method, but I promise you this is probably the quickest one, the simplest one, the one that's going to give you the least amount of headache. And that's our last example. So hooray, this lesson was probably, I think it was the shortest of the whole unit. So it's kind of a nice way to end. There is a homework worksheet to go along with it, working in both directions using proofs, doing an identification of like how to use them. Watch out for this question right here, and this question right here, and this one here. Those ones are good ones to watch out for, and maybe even this one. Okay, so those 4, just be conscious of. You've got some identities to prove, and you've got some questions that kind of match up with that example that we did, or example 2. You've also got some sum and difference identity practice down here as well, so it's not a bad thing to get some extra practice in on. If you are wanting more practice on any of these concepts, please just let me know, and I can easily send that out. Sorry, play around with that. But otherwise, you should be starting to feel pretty prepared. Again, we're not doing a online quest assignment for solving identities, not a big one anyways, strictly because it's just not worth it. I don't feel like you'd be able to show enough work to really warrant that. So just make sure that you're doing these homework worksheets that are available to you on the OneNote and in our class files in Office 365, so that you get practice, and if you do run into problems, you can always ask questions. Otherwise, good luck, and you should be ready to write your test in the next couple of days, so ideally this week.